Imaging dynamic biological processes like a beating heart in 3 dimensions usually forces a brutal trade-off. You either overwhelm living tissue with light or sacrifice temporal resolution. Compressive sensing light sheet microscopy sidesteps this by encoding multiple axial planes into a single camera exposure. But that multiplexing creates a severely underdetermined inverse problem. A recent study tackles this with a plug-and-play reconstruction framework built on ADMM. The modularity is the key innovation. The regularization subproblem is explicitly formulated as a denoising step, meaning you can drop in any off-the-shelf prior, Tikhonov, total variation, BM3D, or modern architectures like FFDNet and DRUNet, without rewriting the solver. The computational win comes from the data consistency update. Because the digital micromirror device applies diagonal binary masks, the forward operator has a structured block diagonal form. Instead of inverting a massive PR by PR matrix, the authors apply the Woodbury matrix identity. This algebraic trick collapses the inversion into a simple P by P diagonal matrix. The result? The update becomes strictly pixel-wise, requiring zero expensive matrix inversions and scaling linearly with image size. Slice-by-slice reconstruction, however, ignores correlations between neighboring optical sections. The authors introduce an axial-coupling term that penalizes interslice discontinuities. This couples the denoising subproblems, so they solve it with a Gauss-Seidel sweep, updating each slice using its most recently computed neighbors. Crucially, they prove subsequential convergence for this scheme under a weakly convex regularization assumption, which guarantees convergence even when the denoiser doesn't correspond to a strictly convex mathematical prior. Experiments on synthetic and real zebrafish cardiac data confirm the theory. Axial coupling consistently improves PSNR and structural similarity, with classical priors seeing the largest relative gains, while deep denoisers achieve near state-of-the-art fidelity. This work proves that combining smart linear algebra with flexible plug-and-play regularization can unlock high-speed, low phototoxicity volumetric imaging. For anyone building computational microscopy pipelines or working on large-scale inverse problems, this framework is a practical blueprint. Check the paper for the full convergence proofs and algorithmic details.